Okay. All right. So during this 2-hour webinar, we will have 3 speakers. Okay. Me, myself, will be the MC as well as the first speaker for today. And please allow me to introduce myself. My name is Nur Haishila binti Muhammad Hirmizi, and currently working as Senior Executive at Centralized Analytical Lab. Previously, I'm graduated from University Science Malaysia for bachelor degree in analytical chemistry, as well as in master in science, majoring in advanced material. Okay, and our second speaker for today is Dr. Che Boyang. Okay, Dr. Boyang, are you there?
Hello, everyone. Yeah, I'm here.
I okay. So Dr. Boyang will be our second speaker for today. He is the application scientist in Horiba Instrument Singapore. So previously, he obtained his PhD in interdisciplinary graduate program under material science and engineering from Nanyang Technological University, Singapore. And our third speaker will be Puan Faizah Isa, lead technologist in Centralized Analytical Laboratory. So Miss Faizah, usually UTP students, if they required for Raman analysis, they will dealing with Miss Puan Faizah. So she's the lead technologist in Centralized Analytical Laboratory, as well as the main PIC for Raman Spectroscopy in CAL. Okay. Uh, okay. All right. So from this webinar, the learning outcome will be all the participant is expected to understand the principles of Raman spectroscopy, will know the key components and working principle of a Raman instrument, as well as know the real world application of Raman spectroscopy, and further understand basic Raman analysis through correct sample preparation, instrument operation, and interpretation of a simple spectrum. Okay, so this is the tentative. The first one will be covered by myself, and the second slot will be covered by Dr. Boyang, and the third slot will be covered by Puan Faizah. Okay, so without further ado, I will continue with our first slot for today. I think everyone is ready. Okay, so the first slot will be on the introduction to Raman spectroscopy, the principles and fundamentals. Okay, so what is Raman spectroscopy? Let me, oops. Okay, so Raman spectroscopy basically is widely known as powerful and non-destructive tool, analytical tool. So it works like giving each material its own unique molecular fingerprints. So like us, human, we also have our own fingerprint, which also differs from others. And our fingerprint is actually identical to our own self. So do Raman spectra. So it provides molecular fingerprint for each material. So that is why it is widely used in diverse field. For example, like I'm highlighting today is in pharmaceutical. So if you can see from this, um, uh, so from this Raman spectra at the left side, okay, where we can see the Raman spectra of loratadine. Okay, loratadine is a antihistamine drugs. Okay, and okay, so we can clearly see the difference between Raman spectra of loratadine and its with its excipient. So from here, from the B spectra, we can observe the loratadine. The C spectra is uh, belongs to uh, magnesium stearate, and the other two will be on the lactose monohydrate and also the cornstarch. Okay. And also in the forensic applications where um, Raman is being used together with other discrimination technique to estimate from the fingerprint, from our fingerprint, it can estimate the sex of the human, the owner of the fingerprint. Okay, right? Okay. So basically, Raman spectra can also be used to differentiate 2D materials. For example, like normally we analyze in our lab is graphene and molybdenum chloride and molybdenum sulfide and so on. Okay, so this is the most this is the most that sample that we received so far lah in our lab. Okay, and the third one, so I think maybe ladies most ladies will love it. All right, for this third application is which is in gemstone. Okay, so we can also use Raman to to actually verify actually and to know what is the type of the gemstones and to know whether it's a pure gemstone or the fake one. So for example, like I think maybe previously we also received external sample. So they would like to know what type of the type of the gemstone and to differentiate the fakes and the pure one. Okay. And then the last one will be on the carbon material. As we all know, carbon exists in so many types of compound. Like for this one, we can use Raman to differentiate whether the carbon is actually is a diamond or graphite or glassy carbon or the most abundance and most cheapest one is the amorphous carbon. Okay, so basically that is some application that being used Raman spectroscopy. Okay, okay, so far so good. Alright, so the next one, okay, what is actually Raman? Uh, so I have shared a few video here just to understand how Raman works. So basically, Raman spectroscopy is a molecular spectroscopy technique where the interaction light between a matter. So when light interacts with matter molecules, most photon will scatter. Okay, so scatter. There are two types of scattering. One is Rayleigh scattering, and another one is Raman scattering. So what is the difference between these two? Right. So Rayleigh scattering the photons scatter elastically, or in other words, the dispersed energy the same with in the incident photon. So which also means the frequency of the scattered photon is the same with the excitation photon frequency. For this, we call it as Rayleigh scattering. And for Rayleigh scattering, uh, we doesn't have not much information on molecules, but the other one for Raman scattering, so basically a very small amount of a fraction of lights. So usually is around approximately around 1/10 million light will be scattered inelastically. This is what we call is Raman effect. And this type of scattering carries unique information about the vibration of the molecules. Okay? Okay, right. So the next one. So Raman scattering, so usually it requires two steps to occur. The first step is a laser photon excites the molecule to a virtual level, virtual level of energy state, and then the molecule relax through release of scattered photon to ground state. Okay, so if for Raman scattering, it consists of two types of Raman scattering. One is Stokes Raman scattering, and another one is the anti-Stokes Raman scattering. So what is the difference between these two? Okay, so basically, the Stokes Raman scattering, the molecule gains energy from the photon during the scattering excited to a higher vibrational level, then the scattered photon lose energy and the wavelength is increased. All right. So this is what we call as Stokes-Raman scattering. So inversely, if the molecule lose energy, okay, uh, for this Raman scattering, by relaxing to a lower vibrational level, the scattered photon gains the corresponding energy and its wavelength decrease. So this is what we call as anti-Stokes Raman scattering. Also, at room temperature, the anti-Stokes Raman scattering is weaker than Stokes Raman scattering. So usually, for the anti-Stokes, usually it is being ignored and removed by filter. Okay, so this is due to interaction between the incident electromagnetic waves and the vibrational energy levels of the molecules in the sample. Okay, so this is the example of the uh yeah, Raman spectrum of carbon tetrachloride. Okay, so it has three pronounced Raman active vibrational modes in the range of 100 to 500 wave number region. Okay, so in the center will be the Rayleigh scatter peak. So basically, this peak is very high. The intensity is very high. So normally it is being blocked by a filter in the Raman spectrometer. Okay, and symmetrically, the Stokes and three anti-Stokes peaks corresponding to the three most intense Raman active vibration of carbon tetrachloride. So it can be seen that the anti-Stokes lines are actually much weaker compared to the Stokes um, lines. Okay, so that is why usually Stokes peak ataupun or Stokes line is usually being used to measure the unique vibrational fingerprint of the sample. So this is the information that we get from a Raman spectra. For example, the first one, the characteristic frequency. So basically, the position of the Raman sheaf. Okay, the graph, the position of the Raman sheaf is we can use it to identify the material using the spectral fingerprint. Okay, while from the intensity, the variation of the intensity from y-axis, basically we can get the information on the concentration of or amount of the material. Okay, this two is the commonly used in our lab. Okay, but for another three, the variation of in intensity with changing laser polarization. So basically, we will get the information on the crystallography orientation. The variation in band position is belongs to the information on the compressive or tensile stress and strain. And the variation in bandwidth is we usually get the uniformity of bond lengths. Okay, for example, the crystallinity. Okay, all right. So from this graph, I think you are quite familiar. Most of us quite familiar with FTIR spectra as well. Okay, so Raman and FTIR is if we see from the graph is quite similar. So both is actually is a molecular spectroscopy technique where use interaction with light and provide information of the molecular. So we discuss a bit the difference between Raman and IR spectroscopy. So basically, for Raman spectroscopy is a scattering phenomena, while the FTIR is actually the absorption of the phenomena. Okay, certain bond, okay, is very sensitive to Raman. So usually for non-polar bonds like C double bond C, S single bond S, SiO Si. So the symmetric molecules, basically we use Raman to analyze it. Okay. But on the other hand, if you have like polar bonds like C carbonyl, C double bond O, the hydroxyl, and the amine. Okay, so basically we analyze it using IR spectroscopy. Okay, all right. So if you have samples like in aqueous samples, so usually it works well in Raman spectroscopy. While as we know, if we have water in sample for FTIR analysis, it will interfere strongly, especially at the range of the uh, 3000 something. Okay, because the peak is very big and broad, so we could not see any peaks. The peaks is overlap, so we could not see the other peak like amines and so on. Okay, so basically, Raman spectroscopy, it requires minimal sample preparation, while FTIR usually requires preparation where we need to use potassium bromide to mix and make this. Although currently we have ATR, so it's much more easier lah compared to KBR method. All right. What is strength of Raman spectroscopy? Like I mentioned earlier, um, it is a non-destructive analysis, and it works with solids, liquids, and gas, and it requires minimal to no sample preparation. It have high specificity, and it compatible with microscopy for spatial resolution. So of course, if you have liquids and gas, you have to have proper sample holder lah to analyze it using Raman spectroscopy. Okay, and of course, it has some limitation and challenges. Uh, like so, usually for Raman spectrum, due to the intensity, the signals or the intensity is very low due to the detector sensitivity, and usually we have interference from fluorescence caused by the laser. So it sometimes is dominate the interference is dominating the sample spectrum, And like for sensitive samples, some of them, the laser that we use, for example, like if we use the power setting is very high, uh, is the power setting is too high, the laser can destroy the section of the sample. Okay. So I think that's all from me. So for the Q&A, we will answer the question at the end of the session. So maybe some of the question will be covered by Dr. Boyang after this. So let's hear from Dr. Boyang first, and then we will answer the Q&A session at the end of the session. So that's all from me. Then I would like to invite Dr. Boyang to proceed with the second slot.
Sure. Let me share my screen. Can you see my slides now?
Yes, we can.
Can, Doctor.
Okay, thank you. So yeah, morning everyone. My name is Bo Yang. I'm the application scientist of Horizon Instruments Singapore. So thank you for inviting me to this a webinar series. And today, following Sheila's talk, I will talk a little bit more on Raman microscope, on working principles, components, applications, and more. So I believe Sheila has done a very good introduction about the working principle. So I will just elaborate a bit more on how what are the different components inside the instrument from the hardware perspective. And from that, we can actually discuss what makes a good Raman microscope. So you will get to know how different components inside a Raman microscope will influence your measurement and your final results. So after that, I will share with you some examples in different application fields. So you will have idea about how the Raman microscope can be utilized in your research and what the real result looks like. And last but not least, I will share with you a little bit on the current limitation of the Raman microscope technique and our Horizon solution to solve this kind of problem and to improve the limitation of the Raman microscope. So today I'm going to talk about these 4 topics. And yes, by the end of today's talk, I will try to answer your questions. So feel free to enter your question in the discussion board, and we'll answer at the end of today's session. So Raman spectroscopy principle, as Sheila has introduced before, so it's actually a scattering phenomenon when we excite a laser on the sample. So we are more interested in so-called the Raman scattering light, which has a different energy level comparing to the laser level. So the energy change is because of the vibration of the molecule. So that's why we can get some chemical information from the Raman scattering light. So the one in cap actually is not a simple Raman spectroscopy, but actually a Raman microscope. So a Raman microscope is the combination of the Raman spectroscopy and optical microscope. So from the Raman spectroscopy part, you will get the spectrum of your result. You will get the chemical information of your sample. And from the optical microscope part, you can get the image of your sample. So by combining these 2 technology, we actually can get more information comparing to the traditional Raman spectroscopy. So here is actually the optical layout of all the components inside the Raman microscope. So I know there are a lot of components inside the instrument. I will just try to get you through from the beginning to the end. And after that, I will just highlight some of the key components inside your Raman microscope. So everything starts with the laser. So we use laser as the light source of the Raman microscope. So when the light comes out from laser, it will go through some filters. So it will go through so-called the band pass filter, and actually to reduce your light source at other wavelengths. It actually narrow down your incident wavelengths. So make sure you get pure signal from your laser, and you will remove those noise. So after going through the bandpass filter, it will go through so-called the natural density filter, or we call this ND filter. It actually help you to reduce the power of your laser. So it could be either like 100% or 10% or 1% of your original full power laser. So this is helpful when you are dealing with those very fragile sample, and if you do not want to burn out your sample, you can use the natural density filter to reduce the power of your laser. So after going through all the filters, the laser light will go to this Raman filter, and it will be first reflected to the microscope part. And when the light goes through the microscope and finally going through the objective lens, it will reach the sample. So this is your sample stage, and the light will have interaction with your sample. So you get all the scattering phenomenon. You have all the Rayleigh scattering, Raman scattering. The scattering will go to all directions. So a portion of the scattering will just go back through the same optical path, going through the objective lens and going through the microscope. And because this time, if you have the Raman signal, it will have the different wavelengths. So this time, this light will go through the filter and reaching the spectrometer part. So just in front of the spectrometer, we will have a pinhole, which you will be able to control the size. And later I will introduce the function of this small hole. And once it enters to the spectrometer part, it will have several mirrors to change the direction of the light. And the light will finally be reflected to the grating. So the grating is the key component inside the spectrometer, and it helps you to disperse your signal. So your signal will be dispersed based on the wavelengths, so that finally your detector will be able to collect all the signals at different wavelengths. So the detector we use will usually the CCD, so that you can capture multiple spectra at the same time. So this is actually how a Raman microscope works. So it goes through all different types of optics inside and finally give you the signal. So now if we use the microscope here, so it's a Raman microscope, right? So we call this a micro Raman because you have the microscope part. So you will be able to reach micrometer spatial resolution. So we call this micro Raman. However, in some cases, you may not really have the microscope together with you. So for example, if you're using a handheld Raman or a probe-based Raman, so we will call this a micro Raman. So it's MACRO. It means we just use the light spot to interact with your sample. And we don't really have very fine control on this light spot. So that you will still can get the spectrum of your sample, but you will not be able to get a lot of spatial information about your sample. And in some cases, we can also replace the microscope with a atomic force microscopy, or we call this AFM for short, and will be further increase the resolution of your Raman result, and we can reach down to nanometer range, then we call this nano Raman. So based on the sampling optics we have, we can have either the micro Raman, the micro Raman, or the nano Raman. So this is just like a brief introduction about components inside the Raman spectrometer, Raman microscope. So now I will just highlight some of the very key components inside. So you should know so that you can optimize the parameter and actually you can improve your final result. So for the laser, so yeah, that's everything. That's actually the most important part, right? So everything starts from the laser. And we do provide different options on the laser, which actually means it can emit out light at different wavelengths. So if a user use a different wavelength laser, if you check the final result, they're supposed to have the same kind of spectrum. So here actually compares the same sample tested by two different lasers, 633 and also 514. So green laser and red color laser. But if you check the final result, actually the Raman spectrum is exactly the same. So your peak appear at the same Raman shift. So this actually shows you the Raman shift result does not change with different laser excitation. So why it's like this? It's because we are not really using the wavelengths, but actually using the Raman shift as the X value of your Raman spectrum. So this is how the Raman shift is calculated. So if you see the equation here, we use the excitation wavelengths to minus your emitted signal. So it's actually not a absolute value. It's a relative value and regarding to your laser. So by doing this kind of calculation, we are able to make sure the Raman shift is always the same, even you are using different wavelengths of the laser. So here is an example to show you that. So if we use the wavelengths as the x-axis, and we test the same sample using 3 different lasers, so blue, green, and red color laser, because they are at different wavelengths, so your signal will be also appear at different wavelengths according to the laser. So if you use 400 plus laser, your signal will start from 400 plus. If you use 600 plus laser, your signal will start from 600 plus. So although you can see the pattern actually is quite similar to each other because it's the same molecule, but the value of your x-axis is different. So you don't really get the same pattern. And it's not good because we try to use Raman as a chemical fingerprint technology, as Sheila has mentioned. So we want the user able to identify the material no matter what light source they're using. So to achieve that, we actually change the x-axis here from wavelengths to Raman shift. So your signal will be calculated, and after you transfer to the Raman shift, you see no matter whether you use blue, green, or red color laser, you always get the same pattern on spectrum, and all the peak are at exactly the same value here. So that's the difference between Raman and other type of spectroscopy technology. So the one difference is actually the X value unit is different. So since all different lasers are supposed to give you the same spectrum, why we still provide so many laser choices? So there are actually several reasons we provide options on lasers. I think one of the main reason, and sometimes you will see on your real sample, is actually we try to avoid fluorescence when we do the Raman test. So here is the same result I showed you just now. So basically, if we test the same sample using 3 different lasers, and if we use the wavelengths as the x-axis, we're supposed to get the same pattern, but just appear at different values. So this is in principle. However, in the real life, what we usually get is this kind of result. So you will see a very strong background under green and red color laser. And this background actually is caused by fluorescence. So Raman is a relatively weak signal, but fluorescence is actually quite strong. So your fluorescence background will cover your Raman peaks. So you will be not able to observe all the Raman peaks if the fluorescence is too strong. So to solve this kind of issue, we will suggest you to use a laser with a higher wavelength, more closer to the NIR. So when we use this 785 laser, you can see the fluorescence is reduced, and we can see more Raman signals from the sample. So that's why we provide different wavelength lasers so that you are able to get rid of the fluorescence interference, and you will be able to observe more Raman signals from your sample. So sometimes when you cannot really get your signal using 532 laser, you will be able to, you can try to shift to another laser, 785 or even higher, to see if you can get a signal or not. So another key component on your Raman microscope is actually the microscope part. So there are a lot of optics inside the microscope, but the one you usually operate is actually the objective lens. So if you have used microscope before, actually I think this is quite familiar to you. So it's similar to all different types of microscope. So on the objective lens, we will have different parameters which describe the property of this lens. So for example, the magnification is something we definitely need to understand because it actually shows you the factor you magnify your image. So if you use your high magnification objective lens, you will see a smaller area, but you will have a bigger factor to magnify your image. So you can see smaller objects using high magnification objective lens. So if you use a small magnification, usually you will try to see the overall picture of your sample because it will actually include more area on your sample surface. So the typical process, actually, we start from the low magnification objective lens. We try to look for the interest area first. Then we zoom in using the high magnification objective lens. Another parameter is called working distance. So it's actually the distance between your objective lens and your sample surface. So for each objective lens, it has a fixed working distance. So when you have to find out this correct working distance when you are trying to test your sample. So usually for low magnification objective lens, you will have a relatively longer working distance. However, for a higher magnification, for example, for 100x objective lens, you will really have a very small working distance. Then you will need to be careful when you operate the instrument because you don't want your sample to touch on your objective lens. So it may cause the contamination on objective lens, and it may also damage your sample. So for some cases, we actually can supply so-called long working distance objective lens so that you will have longer distance between your objective lens and your sample surface. So numeric aperture is another parameter here. So inside this picture is actually this 0.75 value. So it actually kind of describes the efficiency of this objective lens. So this value will determine the light spot on your sample. So it actually determines the spatial resolution of your measurement. So transmission efficiency is the parameter to describe how much light could be transmitted through the objective lens. So usually for visible range, we don't really have to consider about this. But if you are working with UV or NIR light source, then we need to consider to use another objective lens which have better transmission efficiency on that certain wavelength range. So diameter of the lens is basically the size of this lens. So it must be compatible with your microscope so that you can use this objective lens. So for Horiba Raman microscope, so our latest model do have a very unique feature, and I think it's very helpful for your normal operation. Because currently, if you want to use the Raman microscope, and when you change the objective lens, the user have to manually change the parameter inside the software to tell the software, like I'm currently using 10x or I'm currently using 100x objective lens. And then all the parameters will be adjusted accordingly, and you will see the correct scale bar. But now on the latest model, we do have this function called Smart ID. So on each objective lens, we will have a NFC tag, and we do have the NFC tag reader to read each tag. So every time you change the objective lens, the reader will know, so the software will reflect and will just change the scale bar accordingly. So you will never have the mistake on the scale bar of your result. And with the Raman microscope, we can also extend the capability to do the mapping, or we call it Raman image. And to do that, we have to include a motorized stage. So a motorized stage means you can move your stage in both X and Y automatically. And if you have the motorized stage, now we are able to mapping a sample, which means instead of just measuring one single point, now we are able to scanning an area. And within this area, we're scanning point by point with the moving stage. So at each point, you can have one spectrum. And imagine if you have more than one component within this area, then you may have different spectrum at different points. And this different spectrum actually means different type of material. So the final result of the Raman mapping is this kind of color mapping, where each type of color represent one type of material. So from Raman image, you can not only get the chemical information, but also how different components are distributed within your scanning area. So it definitely provide more information comparing to just one single point spectrum measurement. So another key thing about the microscope is the confocality. So if you check this schematic here, it's actually the conventional design of the Raman microscope. The laser comes from here, shine on the Raman filter, and it goes through the microscope. When it reaches the sample, it interacts here, and the signal will goes back and pass through the filter and finally reaching the spectrometer. So the issue of this conventional design is when the laser interact with your sample, so it will not only interact with your focal plane, which is here, the blue color point here, but it will also interact with your top layers. And if the laser is strong enough, it can also interact with your bottom layers. So the laser will interact with your bulk material, and all of the signal will going back through the same optical path and finally reaching the spectrometer. So this actually resulting in more noise of the result. So not only the interested layer, but all layers will give you the signal. So if you're studying the pure material, pure bulk material, then it's fine. But if you're studying like layered or thin film structure material sample, then this will give you a lot of noise. So to solve this problem, we actually add a confocal pinhole just in front of the spectrometer. And this is a very small size hole, and you will be able to reduce and control the size of this hole. So by reducing the size of this hole, it will start to block the signal coming from the top or bottom layer, because only the signal from the focal plane will go through the middle of this hole. So by reducing the size of this pinhole, you start to block those noise. And by doing this, we get less intensity, but we'll get more pure signal from your interested area. So this is a comparison of the two images. One is under the confocal mode, and one is not under the confocal mode. So you can see the difference is on the image quality. So the confocal mode definitely gives you a more clear image comparing to the non-confocal mode. So this is because the noise we get is less. So another useful function on the microscope is the autofocus. So typically users need to do the focus manually by adjusting the knob on the microscope. And in some cases, especially when we are dealing with those samples which is not flat, it will be very difficult to find a good focal point. Because you can see the example here. So if your sample is not flat, if you try to focus in the middle of your image, you will lose focus on the surrounding area because the sample is not flat, so the surface is not on the same height. So if you try to focus on the surrounding area, then you lose focus on the middle part. So it's very difficult for the user to find a very good focus point if the sample is not flat. So now on Horiba, we provide so-called this view sharp function, which is dealing with this kind of not flat sample. So by doing the view sharp, you will be able to adjust the focus on each pixel. So even for the non-flat sample, you will be able to get a very good image like this, so that every pixel is in good focus. And moreover, from this information, because they already record the different height of your sample, so you will finally get this kind of 3D image so that you know the topography of your sample surface. And later in the Raman scan, if you're doing the Raman mapping of this sample, the laser will also follow your surface profile if your sample is not flat, to make sure the laser spot is always shining on the surface of the sample. So your Raman image will be also in 3D format, like this kind of topography. So this, I think, is a very helpful feature for you to do with this kind of rough sample for Raman mapping. Then after the microscope, after the confocal hole, the signal will go to a spectrometer, and the spectrometer is also a very key part inside the Raman microscope. So today I will talk about two parameters about spectrometer. So the first one is the focal length. So the focal length is actually the distance between your grating and your final detector, your CCD. So the grating is the part will disperse your signal based on the wavelengths like this. So if you have longer focal length, so your signal will traverse longer distance, and it will be dispersed wider. So you can see this comparison between the short focal length and the long focal length. So the long focal length will disperse your signal wider. And if we use the same detector to collect the signal, so let's say this detector has 1,000 pixels, and we have 1,000 wave number here. Then for the short focal length, you use 1,000 pixel to collect 1,000 wave number. So 1 pixel is 1 wave number. So this is the spectral resolution you can get. But if you have a longer focal length, because it now disperses wider, so now my CCD can maybe only cover 500 wave number. Then my CCD still have 1,000 pixel. So now for each pixel is related to 0.5 wave number. So which means I actually have a better spectral resolution comparing to the short focal length. So that's the statement here. So if you have a spectrometer with long focal length, you actually have better spectral resolution. So here is the result comparing to measuring the same sample using two different spectrometer. One is 800 focal length, one is 300 focal length. So you can see the blue one, you will have more peaks. For example, this part here, you can see this shoulder using the longer focal length spectrometer, but you won't see this using the shorter ones. Here also the same thing. You can see this shoulder in the blue result, but cannot see in the green result. So longer focal length will give you a better resolution. So once you already have a Raman microscope, the focal length actually is fixed. You cannot really change it anymore. Then how you gonna improve your spectral resolution? So this responding to the second parameter of your spectrometer, which actually the grating group density. So the grating will have a lot of fine grooves on one side, and these fine grooves will actually disperse the light. So depending on the number of grooves on the grating, we usually will give the density as the parameter. So it could be either like 600 groove per millimeter or 1,800 groove per millimeter. So if we use a high groove density, it will disperse the light wider, even though they are traveling the same distance. So if we can use a high groove density, we will able to improve the spectral resolution. So high groove density give you better spectral resolution. So here exactly the same thing. If you see this blue result, which tested under 1,800 groove millimeter, it will show more small peaks comparing to the 600 groove per millimeter. So there are so many optics inside the Raman microscope. So alignment is actually very important. So you have to make sure all the optics are in good alignment so that your instrument is in the best condition for you to function it. So the typical way to do the alignment is usually we will ask our service engineer to go down to the customer site and they will manually align the system for the customer. So now on the latest model, we do have this auto alignment features. So user itself can do the alignment by themselves using the software. So for example, if you see this image here, your laser spot, this green color is your laser spot, it's a little bit shifted from the middle point. And also the shape of this laser spot is not very spherical. So this is actually the indication of the misalignment. So to do the auto alignment, the user just need to click the button in the software and the software will run auto alignment automatically for the user. And within 10 to 15 seconds, it will align the system and move back this laser spot. You can see the animation here and give you the better alignment. So with this feature, actually user will be able to ensure the instrument is always in good condition before their measurement. So that's all the things I would like to share about the hardware part. And then I will share a little bit on the different application examples using the Raman spectroscopy or the Raman microscope. So here I list down 4 different categories. These are fields which we feel are more popular currently. But however, Raman is not only limited to these 4 application fields. Actually, from the example that I will going to show you, actually any application, if you want to get some chemical identification, chemical information of your sample, Raman could be a good candidate. So the first example here is actually on the semiconductor. So this sample is actually a silicon wafer, and we see we use the Raman to map a very large area of this piece of silicon. And because it may contain crystal or amorphous silicon, and the crystallinity will also show difference in the Raman spectrum. So we are able to use the Raman to differentiate between the crystal and the amorphous silicon. So if you zoom in this area here, we actually can find out 3 types of silicon. The red color is crystal silicon, green color is polycrystalline silicon, and yellow color is amorphous silicon. And the next example on the semiconductor is actually on the stress strain measurement. So for the silicon peak, we're supposed to see this peak at 520.7. However, if the silicon material is under compression, this peak will be shifted to the right-hand side. If this peak is under tension, then this peak will be shifted to the left-hand side. So by studying the peak shift, we are able to get the local stress strain information of this silicon sample. So here we map this piece of silicon, and we can find out in the middle triangle region, those peaks are more shifted to the right-hand side. So we know they are under compression. And these red color regions, the peaks are more shifted to the left-hand side, so they are under the tension. So by doing the Raman mapping, we actually can get the local mechanical condition of this silicon material, and it may be related to the failure analysis of this kind of device. So now this example is on the 2D materials. So here we are not doing the Raman, but we're actually using the Raman spectrometer to measure the photoluminescence. So we're actually able to do the photoluminescence using our Raman spectrometer. And here is actually the optical microscope, optical image of this sample. So you can only see a triangle shape. But if we do the PL measurement, we are able to see there are actually 3 different types of samples inside this triangle because they are showing the photoluminescence peak at different wavelengths. So here is for study this 2D material, tungsten sulfide. So polymer is another good sample to test using Raman because the different bond inside the polymer structure we can get very distinct Raman spectra for different type of polymers. So we were able to identify the polymer type using the Raman spectrum. So we can also monitor the polymerization process using the Raman. So here in this case, we put a Raman probe inside the reaction container. And once the reaction starts, we actually can monitor the Raman signal intensity, and we can see the signal from the raw material start to drop, and the signal of the final product start to increase at a certain time. So this actually gives us the polymerization reaction information, and we actually are able to optimize this reaction by changing either the concentration of the sample or by adding the catalysis. So you will see a different reaction rate based on this curve. So microplastic is another application field. So for microplastic research, people are interested to do the particle analysis made by plastic waste. So by doing the Raman, you will be able to get this kind of full information about your microplastic particles. So we do have this software function for you to do very detailed analysis on each particle. And for each particle, you will have all the information, including the location, including the morphology, the size, the diameter and area, the image of the particle, and finally the chemical spectrum of this particle. So you can identify this particle. So you can put out a histogram like this based on the chemical nature. So you will know like how many percentage of the particle are PE, how many percentage are PP, or you can put out the histogram based on the particle size. So you can know how many percentage are below 10 micrometer and how many percentage are above 10 micrometer. So this example here is for forensic, and we are using Raman to identify the ink here. So for this piece of sample, we can compare the ink spectrum to 3 different types of printer, and we can finally determine this piece is coming from this laser printer here because they have the same ink spectrum using Raman. So this example is on the pharmaceutical sample. We are mapping a full vitamin C tablet. So this size is quite big. It's about 20 millimeter. And within this tablet, we have 4 different components. So we can get the distribution of 4 different components here. So we can study how API is distributed within this tablet. And moreover, based on this image, we can also get an estimation about the fraction of the components based on the area it occupies. This example is on the battery analysis. So this is for the cathode material. So for lithium battery, the cathode material, lithium cobalt dioxide, if it starts to degrade, then it will give you this cobalt dioxide peak. So it starts to react and become to another material. So if we map the area of the cathode material, for those, you see this red color region is those area with this small peak here. So the researcher will get the information like why the battery starts to degrade. Maybe because the cathode material starts to degrade, and you know where are the degradation points of your cathode material. So another example here is on anode material. So anode material is usually the carbon materials. So for carbon material, we'll study the DG band. And the DG band ratio is actually a parameter to determine the disorder or the defect of your carbon material. So you can do the Raman mapping before and after the cycling of your battery. And you can see after the cycling of the battery, the DG band ratio increase quite obviously and actually indicates during the cycling, it gives more defects in the anode material structure. So do a very quick summary about the Raman spectroscopy. So from the Raman spectroscopy, we get chemical information, and from the microscope, we get optical image. So the Raman mapping is a perfect combination of these two to show you the component distribution. But however, there is a limitation on the Raman microscope. It's mainly on the spatial resolution. So because it's based on the optical microscope, so the resolution is limited to 1 micrometer. And below 1 micrometer, it will be very difficult for you to see clearly how your sample looks like and get the spectrum. So if you compare different technologies, so optical microscope has the resolution down to micrometer, but there are different type of technology which can go beyond the micrometer and go down to nanometer, like SEM, AFM, or TM. So to improve on the Raman spectral resolution, spatial resolution, we actually are able to combine the atomic force microscopy together with your Raman spectroscopy, so that you can achieve a nanometer resolution. So any of our Raman microscope is able to upgrade to the nano version so that you can do the nanometer scale Raman mapping. So the principle behind this, actually, we are not using the optics to get your Raman signal. However, we use this kind of tip-enhanced analysis. So if you have used AFM before, so all the AFM are tip-based technology. So we scan the sample using a tip. And because the tip is very small, the tip is usually at nanometer range. So you will get a very good resolution. So now in this case, we actually approach the tip on the sample surface very close to each other, and we do not direct the laser to the sample directly. However, we shine the laser on the end of the tip. So when the tip is really close to the sample surface, we'll have this kind of plasmonic effect if we have the correct laser wavelengths and the correct sample substrate. And this plasmonic effect will magnify, will enhance your Raman signal. So you will get your Raman signal coming back to the spectrometer. And because we use tip instead of light spot to interact with the sample, so the resolution you get from this Raman result is also following the resolution of your tip. So it will be down to nanometer. So this is the example to show this kind of capability. So if you are using the nano Raman, so we are able to scan very small size sample. For example, this is a common nanotube. And we'll scan AFM first to get the morphology of this tube. So this is a single tube, and then we can do the Raman mapping. And the mapping will be exactly the same resolution as the AFM. So we are able to get the nanometer resolution here. So in this case, we're starting the DG band, so we can get a little bit information about the defect of your common nanotube along this single tube here. Okay, that's the end of my sharing. Thank you for your time.
Okay, thank you, Dr. Boyang. Right, so we have another slot from Puan Faiza. Then after this, after the third slot, we will answer the question. So everyone, if you have any question, please drop in the comment section, in the chat section. So later on, we will after session Puan Faiza, we will proceed with the Q&A session. Okay, so I would like to invite Puan Faiza to continue with the third slot, which will be covered on the equipment demonstration and sample preparation. Okay, Puan Faiza, you can unmute.
Okay, you hear me?
Yes.
Oh, okay.
Okay. So over to you, Puan Faiza.
Okay. Assalamualaikum and good morning, everyone. Okay, my name is Faiza binti Muhammad Isa. I'm person in charge for Raman Spectroscopy at CAL UTP. Okay, this is our equipment, Raman, brand Horiba, model HR800. Okay, equipment objective, analyze vibrational, rotational, and low frequency modes using Raman scattering, and identify molecular structures, chemical composition, and crystallinity. Okay, this is our equipment setup. Firstly, uh, turn on the main power supply for the laser at top left side. And then number two, I turn the key on at control interface at below right side. And then set the laser emission to the marked level. Usually I use level 1. And then wait for the laser beam to stabilize. Allow around 50 or 3 minutes for warm up. Okay, this is a standard sample. We're using silicon substrate. Okay, this is the video. How to set up first auto calibration. We use silicon substrate. Put the silicon substrate at the stage. Focus the objective by using the cos and phi knob on the right and left hand side of the microscope. Okay, for Raman, we use Spec 6 for the name of the software. Okay, open Spec 6 and then we click the video tab, camera icon on the software window to the video mode. Okay, this time I turn on the Euromax fiber optic light source by rotating the knob and adjust the brightness of the light on the sample. Okay, if we get the brightness, the sample, we can stop lah the adjusting the knob. Okay, then we turn on the Euromax fiber optic light source by rotating the knob. Turn the laser on from the left ramp control box and pull the knob upwards slightly and rotate anti-clockwise. On the first optic column, the spring arrangement on the knob will put it down. At control panel of the software, choose the tab Spectra and click the Spectrum RTD. Okay, during this, the software will acquire the silicon spectrum, identify the peak approximately 52.0 centimeter, and automatically adjust the Raman axis. The x-axis correspond to the Raman shift in centimeter, and the y-axis indicates the signal intensity. Okay, actually, before this, I show for manually set up for calibration. And then after manually completing the measurement manually, we must do it in auto calibration. This is the picture. I show you that step by step auto calibration. Just click the auto calibration and then click current laser grating. After that, we click OK and then wait until auto calibration finish. Okay, this is the result for auto calibration. Okay, I explain a little bit about the graph. Okay, auto calibration performed by using silicon reference that I show you. Under a 514 nanometer laser with a 600 rating. Number two, the spectrum show the characteristic silicon Raman peak at 520.8 centimeter, which is the standard reference position. And then from number three, from this graph, we can see the coefficient obtained 0.00758 is within the acceptable tolerance and the system status marked as pass. And then from the graph, we can confirm that it is accurately calibrated before acquiring graphene or other sample spectra. And then the sharp silicon peak observed at 520.8 validates successful auto calibration. So after calibrate, we get the human auto calibration pass. So I can start proceed the next sample or other sample lah. Okay. Okay, for today, I showed preparation for sample graphene. Okay, this is a sample graphene. Usually, the procedure first, I must clean the glass slide, and then I put a small amount of graphene, and then flatten the graphene sample using a glass slide. Okay, this is after calibrate, then we can go to the next. This is a sample graphene that I observe under optical microscope. Okay, I focus image for graphene. Okay, this is an image of the graphene sample under laser illumination. And then this is the result for graphene. Okay, this result from software Let's Spec 6. Okay, this is the graph. Okay, so we can get the graph. I give the result this standard lah. We give to student, so the student can get this result. So they can know the key Raman peaks for graphene identification, graphene peak. So if you see sharp G band at 1508 centimeter, clear D band 1350 centimeter, and 2D band 2680 centimeter. So this is the graph, and then you can see we use a filter 100x objective, filter 100% objective 100x, and then granting 600 laser. So this is the software give it the result. Okay, the last example student that I received from Carl. Okay, sample we usually we get a sample powder, sample film, solid sample. I think this method. I think this. I'm not sure. This closed sample. I think, and then for our Raman Horiba HR 800, sample can do only sample solid and powder lah. And then, okay, this is the last. That's all from my presentation for equipment setup. Okay. For student, you can subscribe for our YouTube channel, LMG Management. Okay, thank you.
Okay, thank you, Puan Faiza, for the equipment demonstration and also share a bit on the sample preparation. Right, so everyone, we will move on to our Q&A session. Okay, let me scroll up. Okay. The first question, Dr. Boyang. Raman spectra can be used to evaluate only solid powder pharmaceuticals?
Not really. I think in your presentation is already touched on this topic. So Raman could be used for solid, liquid, and gas. So it's just more easier to test solid or powder, but actually we are able to test liquid and gas if you can find a way to, for example, for gas, you need to find a way to trap all your samples inside the container, and it's supposed to have enough concentration. So then when you focus your laser spot inside your container, you're supposed to get the signal from your gas molecule. Yeah.
But from Horiba as well, you have the specific sample holder for liquid and also gas.
Yeah, for liquid, especially for liquid, we do have a accessory, which is more like a cuvette holder. So you are able to prepare your sample inside the cuvette, and then you place the cuvette just inside our, sample holder, and then the laser will be directed to the cuvette and give you the signal from this liquid sample. But in this case, you won't get the optical image if you measure using this liquid holder. So another way actually to test liquid, actually you can try to drop some of liquid on your glass slide, and you place your glass slide under your microscope objective lens. And if you are able to focus on the liquid drop, then you will be able to get your liquid sample signal. Yeah.
So usually that's how we do it, because we doesn't have any liquid holder like a cuvette. So usually we just drop on the glass slide. Okay, the second one, how we may evaluate the polarity of pharma excipients based on Raman spectra. Is there any possibility to evaluate the purity of drugs using Raman? It has another question. Also, is there any possibility to evaluate the polymorphism of drugs using Raman? Actually, different drugs have different solubilities in different solvents. So polymorphism is essential in drug solubility determination.
Okay, I'll try to answer one by one. So, polarity, I'm not sure if it's related to the polarized Raman or not, but if you are interested in the polarized Raman, then we have to add the polarizer inside your Raman microscope. Then you can get the polarized Raman signal. Then from that result, you can get the information about the molecule structure, like molecule orientation of your sample molecule. I know sometimes it's important for pharma application, but basically you do need a polarizer if you want to get this kind of result. And for purity of the drugs will be more easier. It will be more like the chemical identification of your sample. So yeah, you will be able to get, okay, the only requirement is your impurity should be more than enough. I mean, if you are looking about like ppm level, then it will be very difficult for Raman. But if you're looking about percentage level, I think Raman will be able to give you the result that. So it can give you the information about the purity of your drugs. And of course, if you do mapping, it will be more clear. As one of the results I show you just now, if you can map the full tablet of your pill or your tablet, and you will get more information. So if there any purity inside your tablet, you'll be able to see that. And is there any possibility to evaluate the polymorphism? So the answer is yes. So the polymorphism will also show you different peaks. And usually for pharmaceutical application, I guess some of the peaks will appear at a lower value. So usually it will give the difference only maybe below 100 centimeter minus 1. Then you will need a filter to filter out this kind of signal which is close to 0, like what Sheila has mentioned just now. So you maybe need a filter which can give you the anti-Stokes signal, so that you can go to those peaks close to 0 or even negative peaks. But generally, you are able to get the polymorphism information from the drugs. Okay. That's my
Okay.
answer to this question. Yeah.
All right. Okay, the next one, although Arif is asking me, but I think Dr. Boyang is the most expert one. All right, the difference between photoluminescence and Raman peak. Because both
Yeah.
signals will be produced when samples
Yeah.
interact with the high
So
energy laser.
yeah, there are actually two different phenomena. So Raman is a scattering phenomenon. Photoluminescence is more like absorption and emission phenomenon. So I think the key difference is in the principle. So for Raman, we already touched on the principle. So it's basically the scattering of the light, and this light will cause the vibrational mode of the molecule, so you can get the information of the sample. So it's more related to the bond, chemical bond. But for photoluminescence, it's when the light shines on the sample, it actually excites the electrons. So your electrons will be excited by the photoluminescent light source. And when the electrons going back from the excited state to the original state, it will emit out a light, which is the emission light of the PL. So it's two different phenomenon based on two different principles. So that's the main difference I would like to say. And in terms of the application, so Raman is a chemical fingerprint technology. So you can use Raman to identify the material. But for PL, it's not considered as a molecular spectroscopy technology. So this is because it's not so unique as the Raman peaks, which means a lot of the sample may have the similar peak position in terms of PL peak. But PL peak can also be used as a like supporting evidence for you to show the chemical information of the sample. Yeah, so I think that's a combination of these two technology. Yeah.
Right. Then we go to the next question. Can we detect moisture contents by using Raman?
Yeah, so the answer is yes. So we are able to detect moisture contents, as Sheila mentioned also. So water content will be very strong in the FTIR, but in Raman, this peak is not so strong. So we are able to use this peak and analyze this peak. So for study the moisture contents, usually you are looking for the quantitative analysis, which means you need to have some standard sample to build up a calibration curve, which means you need to have a sample like maybe 30%, 50%, or 70% of your water. And then you measure this tree and then you build up. So you take out the intensity of this peak and then you build up this calibration curve. And then you use this calibration curve to predict an unknown sample with unknown moisture content. So this is how usually we use Raman as a quantitative analysis tool. The limitation
For
of
the
Raman, yeah.
Okay, you may proceed.
I'm just trying to answer the second one. The limitation of the Raman in the comparison of FTR or NMR, I won't say it's a limitation. It's more like a difference. So as Sheila also mentioned, so FTIR is dealing with the dipole moment of the chemical bond. So once there's change of the dipole moment, this chemical bond will be FTIR active. But Raman is more like the polarity of this bond. So once the vibrational bond can cause a change in polarity, it will be Raman active. So these two technology are more like complementary technology. So some bonds are FTR active, some bonds are Raman active. So it will be good to test both on your sample to give you full information about your sample. And then for NMR, I'm not really familiar, but I think one of the point for NMR is a destructive method, right? After measurement, you won't have your sample back. But Raman is kind of a non-destructive method. And yeah, that's the thing I can comment on NMR. I'm not really familiar with NMR, yeah.
So basically, these three, we will need to combine all three in order for us to came out with the one molecule structure. So it's a complementary analysis, not uh, another FTIR is better than NMR and or Raman. Okay, maybe I will answer the next question. Elemental analysis between SRF and SPS, which one give better results? I think both give different type of results. SRF you will get in elemental and outside percentage, but SPS you will know in detail the oxidation state. For example, like if we have copper oxide, if you want to know whether the copper oxide is actually copper 2 plus and everything, then you need to use XPS. Okay. All right. The next one. Since hi Dr. Boyan, since you use several filters or mirrors, the laser power will be reduced and not optimized. Is that a disadvantage of the system?
Okay, so you are true on this kind of laser power reduction. So once it goes through a filter or goes through a mirror, you will definitely get some loss of the laser power. But on our latest model, we use this kind of dielectric mirrors. So the efficiency is more than 97%, which means you will have less than 3% loss at every mirror. So overall, at the end of your optical path, when the laser reaching the surface of the sample, you will have at least 50% of your original power. So this is already considered good enough for you to get your signal. So that's the nature of the system, I would like to say, yeah.
Okay, so we have since we have ample time, so we can try to finish up all the Q&A, the question. Is it okay, Doctor?
Sure, no problem, yeah.
Okay, so and the next one, what is the speed of scanning for 3D Raman imaging?
Yeah, that's a very good question. So usually for Raman mapping, not only 3D, even you do the 2D one, it actually takes longer time comparing to the single point measurement, because you can imagine Raman mapping is a scanning area, and you're scanning point by point within this area. So there will be lots of points will be scanned, and on each point you have one spectrum. So the total time of the Raman imaging depends on, first is how many points you want to scan within this area. So this number of points will depend on the step size of each point in X and Y. So if you have larger step size, you will have less number of points, then you will have faster speed. But if you want to have very good quality image, you want to have good resolution, you want to increase number of points, then you of course increase the total measurement time. And the second parameter related is actually the integration time at each point. So this is related to the signal intensity of your sample. So if your sample gives very strong signal, you can reduce your integration time at each point, then you will fasten your total measurement time. But if your sample give very weak signal, you have to increase your integration time, then you will have an increased total measurement time. So in this case, actually our LabRAM Soleil is a very good option here, because first, it's a very sensitive instrument, because all optics we use, just now I mentioned, is very sensitive. It has high efficiency, so you don't really get a very low signal, which means you can reduce your total integration time comparing to your traditional system. And the second point is, on the new system, we do have a function called smart sampling, which actually is a algorithm to help you increase your measurement speed for mapping. So under the smart sampling, we are not scanning from the first point to the last point. We're not scanning from the left to right. Actually, we're scanning starting from those points with more contrast. And more contrast means more features. So we are scanning those points with more information first, and then we'll fill in those details of your image. So by running the smart sampling, you can get your Raman mapping much faster, and you will get the main information first for the mapping. So that's my comment on the speed of scanning for Raman imaging.
The next one, can the system do time resolved luminescence spectroscopy?
So time resolve, I think currently in the system of Cal, we are not equipped with the pulse laser, so we are not able to do the time resolve measurement. So if in the future your instrument can be equipped with the pulsed laser, then we'll be able to do the time resolving.
Or maybe the one in the MIMOS have it?
I don't think so.
Okay.
To the best of my knowledge, they also don't have the pulse laser now. Yeah.
Okay. All right. So question from Dr. Anis Mimos. So she's the one of the PIC for analytical services and receive a wide variety of sample and related to contamination issues. So they have FTIR or PTIR and lab Raman system. So, but sometimes they face challenges in deciding which sample are more suitable for Raman analysis and which are better analyzed using IR. So, could you share some tips or practical guidelines on how to select the most appropriate technique for different types of samples?
Okay, so some tips. So first one, I know some materials are definitely not Raman active. For example, pure metal, you won't have any covalent bond, so there will be non any Raman peaks. And also for some salt like sodium chloride, because they are ionic compound, there's no covalent bond also, so they are not Raman active. So for Raman measurement, at least it should have a certain kind of covalent bond so that it can be measured by Raman. And if you're really using two technology, so I may suggest you try Raman first, because Raman is more easier for you to do the sample preparation. There's no complicated sample preparation required for Raman, and you can still get your sample back after Raman test. So if you are not sure which one is more suitable for you, you can do Raman first always, and then you can try your IR. Yep. I hope I answered your question.
Okay, Dr. Anis. Then what else? From Wan Muhammad Tashrif. So yes, it is possible to analyze liquid sample using Raman, as mentioned earlier. For Sohar, UTP can only we do analyze liquid and solid particles, but I think we never try for gas samples. All this one, the one in the at Cal. I'm not sure whether if it is at different center, then I'm not really well known on the on the equipment. From Arif, what is the special resolution for Raman AFM setting?
So for the special resolution of nano Raman or AFM Raman is depends defined by the AFM part. So depends on the tips you are using for the AFM. So usually for the nano Raman spatial resolution, we can achieve down to several nanometer. So yeah, of course depends on what type of tip you are using. But using our standard one, it will be several nanometer. Yeah.
Okay, from Mr. Azharuddin, for liquid sample, is it suitable to use water immersion objective lens? Do the system need different setup? And then the next question will be, is room light affected the result? Should I switch off the room light when doing Raman and PL? So this is expert from for Raman and PL as well, from Mr. Azharuddin. Okay, so maybe Dr. Boyang can
Yeah.
answer the
So
question.
yeah, our Raman microscope is compatible with water immersion objective lens. So if you are trying to study some object inside water and you want your object lens to be immersed inside, then yes, it's suitable. But you need to have the correct objective lens. So which I believe currently Cal do not really have, right? Yeah. So yeah, if you have the correct one, then you can use the water immersion objective lens for your sample. And then the next question is about the room light. Well, it's a very interesting one. So it's actually not only the room light. In some time, we also even receive some very strange signal from the cosmic rays. So you never know where this light comes from, but it disappeared in the next run. So to answer this question, is room light affected the result? Yes, I think in some degree this does affect the result, and especially if you're testing a silicon or testing a sample, you know the spectrum, and when you see some weird peaks which not supposed to appear in your result, it maybe come from the light sources in the room. So generally, you don't really need to switch off the room light, but when you see some so when you see some weird things, when you see some strange peaks, you can try to switch off the light and see whether this peak is still existing or not. It actually helps you to sort out where these strange peaks come from. Okay.
What else? Oh, from Sohail again. Can Raman detect structural changes in skin lipids or proteins induced by penetration of enhancer like iron liquids? Do you think Raman could be integrated into real-time or in vivo monitoring of drug release and absorption?
This is a very good question. Structural changes in skin lipids or proteins, I think it can. So generally for protein, if they are trying to study the structural changes using Raman, they probably will use the polarized Raman. So they add the polarizer, and then they can get more information about the structure of the molecule so that they can indicate the structural change of the protein. And for your two questions, if you are talking about the real-time or in vivo monitoring, I think you cannot really do using this kind of lab bench Raman. But however, do have a kind of skin probe Raman, which means you can directly use that instrument on human skin, and it's supposed to give you the Raman signal, and it can help you to monitor the signal change along the depth of your skin, so you can see how much your cosmetic product penetrate into your skin. So that is more for the in vivo testing of your sample using Raman. So Raman can do that, and we also have a model for that, but it usually cannot be done using a benchtop one like the one in Cal.
The model that we have is very old model. so actually they have some quite a number of limitation, but we try to maximize whatever that we can do. Okay, I think maybe last two question from Zubair. As you said, sodium chlorides ionic bonds are difficult to analyze. Can we detect volatiles or alcohol-based solvents quantity in liquid samples when it's mixed in sodium chloride aqueous solution and want to skip detection of sodium chloride?
So if you want to detect the alcohol solvent content, then yes, you can, because you will have signal from alcohol, and if you use the method just now I mentioned, you can get the you build up the calibration curve, and you can predict your concentration of alcohol using your calibration curve. So sodium chloride aqueous solution here will just give you nothing. So if you are not interested in this concentration, then it's fine. So you will, as you say, you will skip the detection of sodium chloride. Yes.
Okay, then our last question for today. So from Farhana, can you help for the interpretation of Raman spectra? How can we know each peak belongs to what chemical information, such as band, stretching, structure, etc.? Does the library differentiate and give chemical information for each peak in a single scan of materials?
Yeah, this is a very good question on the analysis part. So generally from the Raman spectrum, the first thing you can do is actually you search inside the database. I'm not sure if if Cal have or not, but
We don't have. We don't have
okay.
that data. We
Yeah,
only
yeah.
have table. So if you want that, I will share the table so you can manually check by yourself.
Yeah, but anyway, if you have the database, you can get identification of the material. So there's actually a lot of actually in the market there are a lot of supplier for the database. But I think for all the Raman database, they won't give you the information like this peak belongs to which bond and which stretching or which structure. So if you really want to dig out all this information, the good way is actually you can try to search the literature. So you should go, I don't know, maybe Google Scholars or what kind of literature database you have, and you can search the material you are testing. And usually there will be researchers who already study this material using different technologies, and they will try to explain like this peak probably coming from what kind of a vibrational mode, coming from what kind of stretching mode. And you can use that as a guide for you to understand how each peak comes from the sample molecule. That's the advice I can give you, because based on my understanding, no library will give you the so detailed information about which peak comes from which bound. Yeah. But I think as a common materials, as a common bond, we do have experience, like for example, for carbon hydrogen bond supposed to have the 3000 range. Like for DJ band of the carbon material is supposed to have like 1400 or 1600. So this kind of information we do have, but if you're talking about the general samples, we do not really have this kind of information. Yeah. Okay.
Okay. I think that's all that we have for the Q&A session. So we've come to the end of the webinar session. So thank you everyone. Thank you Dr. Boyang. Thank you Mr. Lai for jointly organize the webinar with us today. So inshallah from time to time we'll next year we will have another minimum 3 webinar from Carl. So I would like to seek everyone to give some feedback. If you have any other equipments that you would like us to have a webinar on it, so feel free to provide to list out the equipment in the feedback form. So maybe I will share. I will share the link as well at the chat section. Uh,
Yeah, thank you, Puan Sheila, for organizing this seminar. I think it's a very well organized session for every one of us. And I believe, I think everyone, the participants here must have picked up quite a good handful of knowledge. And I also like to thank Dr. Boyang for sharing with us. So so on behalf of High Tech Instruments, we are here to support UTP and all the whoever is interested
users.
on Raman.
Mhm.
Yeah. So we are happy to organize seminars like this. So yeah, Puan Sheila, if you want to make it this a yearly event, I think it should be no problem for us. Is
And
that okay, Dr. Boyang?
so maybe in the next
Yes. Okay.
webinar series we will cover more on the analysis, because for this time around we focus on the instrumentation, the equipment setting. So maybe next one will be more on the results analysis. Maybe.
Yeah. Yeah,
Okay.
that'll be nice. Yeah, sure. Just let
Yeah,
me
of
know.
course. Okay. Of course, the turn is we also have good support from high tech all this while. Okay.
Thank you,
All
Dr.
right.
Anis.
So I think that's all for today. Have a good day, everyone. Thank you so much for attending this webinar, and we will see you in the next session. And if there's anything, I've shared Carl official email. So if anything, you can just drop. Oh, gambar. Okay. All right. So
Oh, gambar.
gambar. So
But how to fit everyone? Boleh ke? Few screens lah. You know, screenshot.
I think Sheila's line is disconnect.
Yeah, I guess so. Yeah, probably we'll just wait for a while.
Ada tu, kejap. Naim ni dia. Ada tu, Sheila ada tu, kejap.
Ada eh?
all hang pula. Can I boleh tolong tak?
Kan Naim background Makmal lah.
It's
Sekejap.
okay.
Sekejap.
I'm using the laptop, but I'm using two device, but in the laptop is hang pula.
Do you need
So-
everyone to just on the camera so that at least you have the face?
Kena on video. Sorry, kena on camera.
Dekat je snapshot.
Kat mana? Jom silang
Dekat belakang.
Yeah, maybe we like to request everyone to just on their camera if you're confident enough. Is okay with you?
Sekejap, boleh nampak semua ke?
Kena scroll lah. Mungkin ada kena ada 5 page.
Kejap, I nak kena tengok. Kalau yang ni dia dapat tak?
I punya macam gelap.
Kejap, I tengok. Yang ni dapat berapa? Tu dah penuh dah ni. Kejap, control print screen. Apa?
Dapat ke?
Nampak? Kejap, together mode.
Kan Aim dapat tengok semua frame.
Kejap, dia macam ada dua page juga.
2 page lah. Screenshot 2 page lah.
Kejap. Tu. Sekejap. Sekejap ya. Cik. Bagikan screenshot tu tengok, tak dapat lagi.
Screenshot, kata screenshot menu kan?
Ke Ija boleh screenshot? Cuba try.
Tak, okay.
Kat lab ni pun internet dia macam bercinta.
Dapat, okay.
Okay. 1, 1, 2, 3. Sekejap. Again, 1, 2, 3.
Boleh je, dapat.
Sekejap. Kesukaan awak tu. Nombor 2. Okay, 1, 2, 3. 1, 2, 3.
Okay, 2 page.
Sebab ramai kena tu. Kena banyak muka surat.
Banyak muka surat.
This one. Okay. Okay, so that's all. Thank you, everyone. That's all from us. So hope to see you again in the future and have a good day. Bye, everyone. Assalamualaikum. Thank you, Dr. Boyang.
Thank you,
Mr.
Dr.
Thank
Boyang.
you, Puan Sheila,
Thank
Puan
you.
Faizal.
Thank you.
Thank you,
Thank you
Mr.
for
Lai.
organizing this
Thank you.
one.
Thank you all.
Yeah, looking forward for the next session.
Okay.
All right. Thank you for all the
Okay.
participants for joining in. Goodbye. Have a nice
Bye.
day.